The Industrial Revolution in Europe represents a long-term transformation in methods of production, technological innovation, economic structures, and social organization, commencing in the mid-18th century and continuing until the outbreak of the First World War in 1914. Historians widely recognize that the process did not occur uniformly across the continent, but began in Britain between approximately 1760 and 1780, subsequently diffusing to continental Europe and other regions over the following decades. Industrialization during this period is defined by the transition from manual production and traditional agrarian economies to mechanized manufacturing, factory-based labor, and energy-intensive industrial operations, accompanied by substantial demographic and urban transformations. The periodization of the Industrial Revolution is generally divided into two major phases, though transitional and overlapping developments complicate exact chronological boundaries. The first phase, often referred to as the Early Industrial Revolution, spans from the mid-18th century to the 1830s, and is characterized by the mechanization of textile production, the initial use of steam power, and the expansion of coal and iron-based industries. Britain led these developments due to its abundant coal and iron resources, advanced agricultural systems, developed financial institutions, and access to colonial markets. Innovations such as the spinning jenny, the water frame, and later the steam-powered spinning mule revolutionized textile manufacturing, while James Watt's improvements to the steam engine provided a reliable and adaptable source of power for factories and mines. The early Industrial Revolution also saw incremental changes in metallurgy, including the increased use of coke in iron production and the refinement of blast furnace techniques. The second phase, frequently labeled the Second Industrial Revolution, or the phase of technological intensification, extends roughly from 1850 to the outbreak of World War I in 1914. This stage is marked by the expansion of industrialization beyond Britain to continental Europe, encompassing Belgium, France, the German states, northern Italy, and later Eastern Europe. Key technological advances include the mass production of steel using Bessemer and open hearth processes, the emergence of chemical manufacturing industries, and the development of electricity generation and distribution for industrial and domestic use. The period also experienced the proliferation of rail networks, telegraph communication, and mechanized transport systems, which facilitated industrial growth and the integration of national and regional economies. In this phase, industrial corporations and joint stock companies grew in scale and complexity, supported by the rise of formal banking systems and credit institutions. Governments increasingly influence industrial development through infrastructure investment, technical education policies, and regulatory frameworks. Historiographical debates emphasize that the Industrial Revolution should not be understood solely as a British phenomenon, but as a complex European transformation shaped by regional variations in natural resources, labor availability, institutional frameworks, and state policy. In Britain, industrialization was accelerated by high coal deposits concentrated in areas such as the Midlands and Northumberland, navigable rivers, and proximity to ports facilitating international trade. Continental Europe experienced more heterogeneous industrial growth. Belgium's early industrialization was concentrated in Wallonia, particularly in the Sillen Industrial, where coal and iron resources were accessible. The German states underwent significant industrial expansion following the Zollverein Customs Union of 1834, which facilitated the free movement of goods and capital across the region. France developed a mixed industrial profile, combining artisanal and mechanized production, while northern Italy saw limited early industrialization due to political fragmentation, but experienced significant growth in textiles and mechanical engineering by the late 19th century. The European Industrial Revolution fundamentally reshaped patterns of labor and demographic distribution. Population growth between 1750 and 1850 was facilitated by improvements in agricultural productivity, such as crop rotation, selective breeding, and the introduction of new crops, including potatoes and maize, which increased caloric intake and supported urban populations. As industrial production concentrated in urban centers, cities such as Manchester, Birmingham, and Liverpool in Britain, and later Lille, Lyon, and the Ruhr region in continental Europe expanded rapidly. Urbanization resulted in both opportunities and challenges. Wage labor replaced home-based work, new social classes emerged, and public health infrastructure struggled to keep pace with population density. By 1850, a significant proportion of the British population was employed in manufacturing, mining, and transport, marking a departure from agrarian employment patterns that had dominated for centuries. Industrialization was driven by technological innovation and the cumulative adoption of mechanized processes across multiple sectors. In textiles, mechanization reduced reliance on skilled artisans while increasing output and consistency. In metallurgy, the shift from charcoal to coke enabled higher volume iron production and the construction of more robust machinery and infrastructure, including railways, bridges, and factory buildings. Coal mining expanded to meet energy demand, with production in Britain increasing from approximately 6 million tons annually in 1750 to over 100 million tons by 1850. The rise of steam power extended mechanization to areas previously constrained by geographic limitations, including inland regions lacking sufficient water flow. The integration of steam-driven machinery in multiple sectors created economies of scale that reinforced industrial growth and capital accumulation. Economic organization evolved alongside technological and demographic change. The early 19th century witnessed the emergence of factory systems that centralized production and enforced coordinated labor practices. Work schedules became regimented, output quotas were introduced, and specialized machinery required collective management and maintenance. As industrial production intensified, entrepreneurs increasingly utilized joint stock companies, investment banks, and insurance markets to mobilize capital for large-scale industrial projects. The development of financial markets facilitated the construction of railways, canals, and factories, supporting long-term industrial growth. Governments played a complementary role by establishing patent laws, providing technical education, and investing in public infrastructure, such as ports and rail networks, to reduce logistical constraints and promote competitiveness. The European Industrial Revolution cannot be separated from global trade and colonial networks. Raw materials, including cotton from India and the southern United States, copper from Chile, and rubber from Southeast Asia, fueled European industrial operations. Conversely, European manufactured goods found markets in Asia, Africa, and the Americas, fostering an increasingly interdependent global economy. By the mid-19th century, Britain's industrial output accounted for approximately 40% of global manufacturing, with textiles and iron products dominating exports. Continental European industrialization followed a similar pattern, albeit at varying scales, with Belgium, France, and the German states integrating regional resources and external trade networks into industrial systems. The social implications of industrialization extended beyond labor organization to education, gender relations, and political structures. Mass production and factory employment created demand for a literate and technically competent workforce. State-supported technical schools, apprenticeships, and vocational training emerged in Germany, France, and Britain to meet these needs. Women increasingly participated in the labor force, particularly in the textile and garment industries, while child labor remained a significant component of early industrial employment, prompting initial legislative interventions in the 19th century. The rise of industrial wage labor influenced social hierarchies, contributed to the development of labor unions and cooperative societies, and fostered early social reform movements addressing working conditions, housing, and public health. By the late 19th and early 20th centuries, industrialization had transformed both the material and organizational landscape of Europe. Steel production, chemical manufacturing, electrification, and mechanized transport became central to national economies. Urban populations outnumbered rural populations in many regions, and industrial corporations exercised substantial influence over economic and political life. The period immediately preceding 1914 was characterized by intensified international competition, technological standardization, and large-scale infrastructure projects such as railway networks, electric grids, and urban sanitation systems. Industrialization remained uneven geographically, with Southern and Eastern Europe lagging behind Northern and Western regions. Yet the cumulative effect of technological, economic, and social change had reshaped the European continent and established the structural foundations for modern industrial economies. Throughout the period from 1760 to 1914, the Industrial Revolution in Europe was a dynamic, multi-phase transformation involving the interplay of technology, capital, labor, and state policy. It began in Britain with mechanized textile production and steam power, expanded to metallurgy and transport, and later encompassed the industrialization of continental Europe through the Second Industrial Revolution. The revolution was underpinned by quantitative growth in output, energy consumption, population, and urbanization, and it entailed profound social, economic, and institutional changes. By the outbreak of the First World War, the pre-war industrial order, characterized by mass production, mechanized transport, and integrated national and global supply chains, had reached maturity, marking the widely recognized endpoint of this extensive European transformation. The period preceding the Industrial Revolution in Europe, often referred to as the Proto-Industrial phase, spanned roughly from 1600 to 1760. During this time, the foundations of later industrialization were established through demographic growth, agricultural innovations, the expansion of cottage-based manufacturing, the accumulation of capital, and the development of regional and international trade networks. This era laid the structural, technological, and social groundwork that allowed mechanized industry to emerge in the mid-18th century, particularly in Britain and eventually across continental Europe. Demographically, Europe experienced sustained population growth during the 17th and early 18th centuries, though patterns varied regionally. In Britain, the population increased from approximately 5.5 million in 1600 to nearly 6.5 million by 1700, and then to over 7.5 million by 1750. Similar trends were observed in the Low Countries and parts of Germany and France, although regions affected by warfare, famine, or disease exhibited slower growth. Improvements in agricultural productivity were a significant factor enabling this demographic expansion. Agricultural output increased through the adoption of techniques such as crop rotation, including the four-field system widely implemented in England by the 18th century, which replaced fallow periods with nitrogen-fixing crops like clover and turnips. Selective breeding of livestock, particularly cattle and sheep, enhanced meat, milk, and wool production, contributing to higher food availability and the generation of surplus for market exchange. The introduction of new crops from the Americas, including potatoes and maize, provided calorically dense alternatives that supported population growth, particularly in Northern Europe. Alongside these agricultural developments, the period saw significant changes in rural labor structures and proto-industrial production systems. Cottage industries, also known as the putting-out system, became prevalent, particularly in textile-producing regions such as East Anglia in England, Flanders in the Low Countries, and the Rhine region of Germany. In this system, merchants supplied raw materials, typically wool, flax, or cotton, to rural households, which processed the fibers into yarn or woven textiles. The finished products were then collected by the merchants for sale in domestic or international markets. By the mid-18th century, it is estimated that in parts of England, over 50% of rural households participated in some form of textile production, demonstrating the extensive integration of household labor into proto-industrial networks. These systems allowed for the distribution of production geographically, reducing dependence on urban centers while cultivating a skilled workforce accustomed to organized labor processes, time management, and material handling. The expansion of proto-industry was closely linked to the availability of capital and the development of merchant networks. Commercial accumulation was facilitated by European overseas trade and colonial ventures, which generated profits that could be reinvested in productive enterprises. In England, the wealth acquired from the Atlantic trade, including wool, sugar, and tobacco, enabled merchants and landowners to finance larger-scale textile operations and invest in experimental technologies. Credit networks and local banking institutions in regions such as London and Amsterdam allowed for the financing of raw materials, shipping, and early machinery, establishing a financial infrastructure that would later support industrial expansion. Continental Europe similarly experienced merchant-driven industrial growth. In Flanders and northern Italy, urban elites invested in proto-industrial ventures in rural regions, while in the German states, guilds and merchant associations facilitated the distribution of materials and the marketing of finished goods. Technological experimentation during the proto-industrial period focused primarily on incremental improvements to existing production methods rather than the mechanization that would later define industrialization. In textile spinning and weaving, innovations such as the stocking frame, invented in 1589 by William Lee in England, and later improvements to hand looms and spinning wheels, increased output and reduced labor requirements. Water power began to supplement manual labor in small-scale mills by the early 17th century. By the 1720s and 1730s, water-driven fulling mills, grain mills, and small textile workshops were increasingly common in England, Belgium, and the German states. These early uses of mechanized power established the technical understanding and engineering practices that would underpin later steam-powered industrialization. Urbanization during the proto-industrial phase was modest but significant for creating nodes of commercial and artisanal activity. Market towns and small cities became centers for the processing, trade, and distribution of rural-produced goods. In England, towns such as Manchester, Leeds, and Norwich experienced population growth tied to textile production, even before factory-based industrialization. In continental Europe, urban centers in Flanders, northern France, and the Rhineland served similar functions. The concentration of skilled artisans, merchants, and transport infrastructure in these towns facilitated the diffusion of innovations and provided a ready labor pool for the eventual rise of factories. Government policy and institutional frameworks also played a role in shaping the preconditions for industrialization. In Britain, legal structures protected property rights and contractual arrangements, providing merchants and landowners with confidence to invest in production and technological experimentation. Patent laws, including the Statute of Monopolies, 1624, and subsequent expansions, encouraged inventive activity by granting exclusive rights to technological innovations. On the continent, states varied in their support of proto-industry. The Dutch Republic promoted international trade and urban enterprise, while certain German principalities and Italian city-states encouraged guild regulation and apprenticeship systems that provided structured technical training, albeit with more restrictive controls on production. In France, mercantilist policies under Colbert and his successors sought to stimulate domestic manufacturing and maintain competitive advantages in textiles, metallurgy, and luxury goods. Transport infrastructure during this period remained limited but was undergoing gradual improvement, providing the logistical support necessary for proto-industrial operations. Rivers and canals were critical for the movement of bulk goods, particularly in England, the Low Countries, and northern Italy. By the early 18th century, canal construction was increasingly used to connect inland production areas to ports and urban markets. Roads remained rudimentary in many regions, though turnpike trusts in England facilitated incremental improvement of road networks from the 17th century onward. Merchant fleets and river transport enabled proto-industrialists to access international markets, linking rural production with colonial and European consumers. This integration of production, transport, and trade helped cultivate the commercial and logistical skills necessary for large-scale industrial operations. Energy utilization in proto-industry was predominantly based on human and animal labor, supplemented by water power. Early experiments with water wheels and simple mechanical devices increased efficiency in spinning, weaving, and milling operations. Yet energy availability remained a constraint, limiting production scale. Coal use was localized and primarily for heating or small-scale industrial applications, as the full exploitation of coal as an industrial energy source would emerge only with the development of high-pressure steam engines in the latter half of the 18th century. Nevertheless, familiarity with water-driven machinery provided the technical and conceptual foundation for the subsequent integration of steam power into industrial production. Social structures during the proto-industrial period were gradually shifting in response to demographic, economic, and labor changes. Rural households engaged in putting out systems experienced partial commercialization of subsistence economies, generating supplemental income and fostering engagement with markets. Skilled artisans in towns maintained guild-based control over production, while a growing class of merchants and entrepreneurs coordinated the distribution of goods, capital investment, and labor allocation. Wage labor coexisted with household production, introducing early forms of labor discipline and time management. These social arrangements created a workforce accustomed to regularized work and commercial exchange, which would be essential for the operation of centralized factories in the coming decades. International trade and colonial networks increasingly influenced proto-industrial activity. Britain, the Low Countries, and northern France relied on imports of raw materials, particularly cotton, which began to supplement wool and linen in textile production. Colonial connections facilitated access to overseas commodities such as sugar, tobacco, and cotton, which stimulated demand for manufactured goods and created incentives for the mechanization of production. Continental Europe also participated in international trade, though with greater regional variation. Belgian and northern Italian merchants exported textiles to European and Mediterranean markets, while German producers sold metalwork and cloth within the fragmented political landscape of the Holy Roman Empire and adjacent states. By the mid-18th century, the combination of demographic growth, agricultural improvements, proto-industrial production, accumulation of capital, technological experimentation, and expanding trade networks had established the structural prerequisites for industrialization. Britain, with its extensive coal and iron resources, developed financial markets and integrated colonial trade networks, and was particularly well-positioned to initiate mechanized industrial production. Continental Europe possessed many of the same preconditions, though the pace and extent of early industrialization were constrained by political fragmentation, regional resource distribution, and varying institutional support. In quantitative terms, proto-industrial production in Britain alone had reached significant levels by the 1750s. Textile output in East Anglia and the West Midlands, measured in raw spun yarn, increased by approximately 50% compared with the first half of the 17th century. Similarly, small-scale metalworking and mechanical workshops in urban centers such as Birmingham expanded output to supply local and regional markets. Population in proto-industrial districts often grew faster than in purely agrarian regions, reflecting the attraction of supplementary income opportunities and the early concentration of labor in towns and production villages. Capital accumulation and merchant networks provided both credit for raw materials and investment in experimental technologies, including early water-driven mills and mechanized looms. The integration of these preconditions established both the technological capacity and social organization that would underpin mechanized industrialization. Households accustomed to producing standardized goods for markets, merchants experienced in coordinating supply chains, and regions with sufficient labor and energy resources created a networked system ready for transition. Water-driven mills, early spinning machines, and experimental metallurgical processes developed the technical expertise and engineering knowledge necessary for the introduction of steam power, mechanized iron production, and factory-based labor coordination. The proto-industrial period also fostered social and institutional frameworks capable of absorbing industrial change, including legal protections for property and contracts, guild and apprenticeship systems, and nascent forms of financial and commercial regulation. The mechanization of textiles in Europe during the 1760s through the 1790s represents the initial large-scale industrial transformation of production methods, marking the beginning of the Industrial Revolution. This period is characterized by the development and adoption of mechanized spinning and weaving technologies, the concentration of production in factory systems, and the transition from dispersed domestic manufacture to centralized industrial organization. Britain served as the primary site of these innovations, driven by regional concentrations of skilled labor, access to raw materials, a growing population, and favorable economic and institutional conditions. Continental Europe, while slower to mechanize, observed and gradually adopted these technologies during the latter part of the 18th century, particularly in Belgium and northern France. Textile production before mechanization relied heavily on the putting out system, in which rural households spun yarn and wove cloth using manual tools. By the mid-18th century, increasing demand for cotton goods, both domestically and internationally, placed pressure on the limitations of manual production. The introduction of mechanized devices for spinning and weaving increased output and reduced the dependence on skilled artisanal labor. Among the earliest and most influential devices was the spinning jenny, invented by James Hargreaves in 1764 in Lancashire, England. The spinning jenny allowed a single worker to spin multiple spools of yarn simultaneously. Early versions operated with 8 spindles, which expanded to 80 or more by the 1780s. This increased productivity by a factor of approximately 10 to 20 over traditional hand spinning, significantly lowering labor costs and enabling more rapid production of yarn for weaving. Concurrently, Richard Arkwright developed the water frame in 1769, which utilized water power to drive multiple spinning rollers and spindles. Unlike the hand-operated spinning jenny, the water frame required a fixed location near a water source, effectively encouraging the creation of purpose-built mills. Arkwright's water-powered mills represented a fundamental shift in production organization as they centralized labor and mechanized energy sources, laying the groundwork for factory systems. By the 1780s, Arkwright and his partners operated dozens of mills across Lancashire, employing hundreds of workers, including women and children, who performed tasks in regimented schedules and coordinated production processes. The spinning mule, developed by Samuel Crompton in 1779, combined features of the spinning jenny and the water frame, producing finer and stronger yarns suitable for high-quality textiles such as muslin and calico. The spinning mule increased both the speed and consistency of production, allowing for the mass production of yarn at scales previously unattainable with hand labor. By the 1790s, spinning mules were in widespread use across Lancashire, powering significant expansions in cotton textile output. Estimates indicate that between 1760 and 1800, the production of cotton yarn in Britain increased from approximately 500 million pounds annually to over 2,500 million pounds, illustrating the transformative impact of mechanization. Weaving, while initially lagging spinning and mechanization, also underwent significant technological development. The flying shuttle, patented by John Kay in 1733, allowed a single weaver to operate a loom at twice the speed of manual weaving. Later in the 1780s and 1790s, powered looms began to emerge, including prototypes utilizing water or horsepower to drive mechanical weaving mechanisms. The combination of spinning and weaving mechanization led to a significant reduction in production bottlenecks, enabling the establishment of integrated textile factories where multiple stages of production occurred under one roof. This system allowed for the coordination of labor, maintenance of consistent quality, and expansion of output, setting a precedent for industrial manufacturing in other sectors. The mechanization of textiles in Britain had profound socio-economic implications. Factories required concentrated labor forces, prompting migration from rural areas to urban and semi-urban industrial centers. Towns such as Manchester, Bolton, and Blackburn experienced rapid population growth, with Manchester's population increasing from approximately 75,000 in 1750 to over 180,000 by 1800. The concentration of labor in factories necessitated the introduction of new labor discipline practices, including fixed working hours, supervision of tasks, and hierarchical organization of workers. Women and children became central to textile labor, accounting for a substantial proportion of the workforce, with estimates suggesting that in some Lancashire mills, over 60% of employees were female or under the age of 16. Wages for factory workers varied by skill and age, but were generally lower than rural earnings, though consistent employment allowed families to achieve greater economic stability compared with seasonal agricultural labor. The spatial concentration of textile production also influenced regional infrastructure. Water-powered mills required construction near rivers and streams, while later steam-powered innovations facilitated urban factory placement. To support the distribution of textiles, transport infrastructure such as roads, canals, and navigable rivers was improved, enabling products to reach domestic and international markets more efficiently. In Britain, the development of the Bridgewater Canal, opened 1761, exemplifies this integration, connecting coal supplies to industrial centers and lowering transport costs, which indirectly supported textile production. Merchants, financiers, and mill owners coordinated capital investments, raw material procurement, and market distribution, establishing early industrial supply chains and networks that were later replicated in continental Europe. Mechanized textile production in Britain also stimulated advances in related industries. Cotton and wool processing required carding, combing, and bleaching, processes increasingly mechanized using water-powered or horse-powered devices. The iron industry supplied machinery components, including spindles, gears, and shafts, driving further demand for iron and facilitating technological interdependence between sectors. Coal mining expanded to meet the energy needs of water-powered and later steam-powered mills. By the end of the 18th century, coal output in Britain had increased to over 20 million tons annually, supporting both domestic industrial use and urban consumption, forming the energy backbone for subsequent mechanization across industries. In continental Europe, the mechanization of textiles followed Britain's lead, albeit with regional variations and temporal delays. Belgium, particularly in the Walloon region, adopted water-powered spinning and weaving mills in the 1780s and 1790s, driven by local coal and iron resources and supportive state policies under Austrian administration. In northern France, proto-industrial textile centers such as Lille and Roubaix began experimenting with mechanized looms and spinning devices in the 1780s, often relying on local merchants to finance the construction of mills. German states, fragmented politically and economically, saw the initial adoption of water-powered textile machinery in regions such as Saxony and the Rhineland. Early continental mills were typically smaller in scale than their British counterparts, reflecting differences in capital accumulation, labor availability, and institutional support, but they nonetheless represented a critical step in industrial diffusion. The introduction of mechanized textiles also had international trade implications. Britain's production of cotton cloth increasingly met domestic and colonial demand, while exports to continental Europe and the Americas expanded. Between 1760 and 1790, British cotton exports grew from approximately 3 million yards annually to over 20 million yards. The availability of high-quality, mechanized cotton textiles influenced global market patterns, increasing the competitiveness of British manufacturers and stimulating continental producers to adopt similar technologies. Raw cotton imports primarily from India and the southern United States rose dramatically, with Britain importing over 100,000 tons of raw cotton annually by the end of the 18th century, reflecting the integration of industrial production with colonial trade networks. Mechanization also influenced labor organization and social structures. In factory settings, tasks were subdivided into specialized operations, reducing the reliance on multi-skilled artisans and enabling less skilled workers to contribute effectively. The implementation of strict production schedules, hierarchical supervision, and standardized procedures established early forms of industrial discipline. Apprenticeships, long a feature of artisanal systems, were supplemented by in-factory training programs to develop necessary skills for operating machinery. These developments not only increased productivity, but also shaped the labor culture and social experience of industrial communities, laying the groundwork for later labor movements and regulations. The mechanization of textiles during 1760 to 1790 represents the convergence of technological innovation, capital investment, labor organization, and market integration. British leadership in this transformation was reinforced by its concentration of coal and iron resources, extensive waterway networks, access to colonial markets, and institutional support for commercial activity. Continental European adoption, although slower, demonstrates the transmission of technological knowledge and industrial practices across borders. The increase in output from both hand-operated and mechanized production reshaped the textile economy, stimulated complementary industries, and established patterns of labor and capital organization that would define the broader industrial revolution. Quantitative indicators underscore the magnitude of transformation during this period. In Britain, the number of spinning mills rose from fewer than 20 in 1760 to over 120 by 1790. Employment in cotton manufacturing increased from approximately 50,000 workers in 1760 to over 200,000 by the close of the century. Output per worker expanded as mechanized spinning and weaving devices multiplied production rates tenfold in many cases. Energy consumption, initially dependent on water power, began to shift toward coal and later steam power, establishing the energy foundations for full industrial mechanization. By the 1790s, mechanized production accounted for a majority of cotton yarn output in Britain, while hand spinning remained significant only in smaller, rural districts and in countries outside Britain that had yet to mechanize. In addition to technological and economic impacts, mechanized textiles influenced regional economic specialization. In Britain, Lancashire became the preeminent center of cotton manufacture, while Yorkshire specialized in woolens and Scotland's lowlands focused on linen and cotton blends. Continental Europe similarly exhibited regional specialization based on resource availability, labor skills, and existing production networks. Belgium's Wallonia focused on cotton and wool processing, northern France on cotton cloth for both domestic and export markets, and Saxony and the Rhineland on mechanically spun and woven goods. This regional specialization facilitated industrial clustering, technological diffusion, and competitive advantage in international markets. By the end of the 1790s, the mechanization of textiles had transformed both the methods and scale of production, the organization of labor, and the economic geography of Europe. The innovations of Hargreaves, Arkwright, Crompton, and Kay provided technical solutions that accelerated output, reduced costs, and enabled factory-based production. The integration of capital investment, skilled labor, and mechanized machinery established the operational model for subsequent industrial sectors. Mechanized textiles not only increased Britain's industrial capacity, but also influenced continental European industrial development through knowledge transfer, migration of skilled workers, and trade networks. Collectively, this period laid the technical, economic, and social foundations that would support the expansion of industrialization across Europe in the following decades. The period from 1769 to 1830 marked a decisive transformation in European industrial energy systems with the development and widespread adoption of steam power, which provided a reliable and adaptable source of mechanical energy independent of traditional water and animal labor. Steam power not only enabled the expansion of mechanized textile production, but also revolutionized mining, metallurgy, transport, and a wide range of industrial applications. Britain led the initial innovations, with James Watt's improvements to the steam engines serving as the foundation for the industrial adoption of thermal engines, while continental Europe gradually integrated these technologies into local production and infrastructure. The conceptual and technical evolution of steam power began in the late 17th and early 18th centuries with Thomas Newcomen's atmospheric engine. Introduced in 1712 for the purpose of pumping water from mines in Cornwall in northern England. While effective in removing water from coal and tin mines, Newcomen's engine was limited by low thermal efficiency and large coal consumption, producing roughly 0.5 horsepower per engine and requiring continuous supervision. The primary value of the Newcomen engine was its demonstration of converting heat energy into mechanical motion, a principle that would be refined and expanded by later engineers. James Watt's contributions, beginning in the 1760s, addressed these limitations and transformed steam power into a practical energy source for industrial production. Watt's innovation included the separate condenser, introduced in 1765, which reduced energy loss by maintaining the cylinder at a lower temperature than the condenser, substantially improving fuel efficiency. Subsequent refinements, including the rotary motion adaptation around 1781, allowed the steam engine to drive machinery directly, rather than solely performing reciprocating tasks such as pumping. By 1800, Watt and his partner Matthew Boulton had installed hundreds of engines across Britain, powering textile mills, ironworks, and breweries, with each engine capable of delivering multiple tens of horsepower, depending on design and scale. The adoption of Watt's engines coincided with increased coal production, which rose from approximately 20 million tons annually in 1760 to nearly 50 million tons by 1800, ensuring an adequate energy supply to sustain industrial growth. The introduction of steam power facilitated the spatial concentration of factories and industrial operations. Whereas water-powered mills were constrained by river location, steam engines allowed mills and workshops to be situated in urban centers with access to labor, transport networks, and markets. For example, textile mills in Manchester increasingly relied on steam engines for spinning and weaving machinery by the 1790s, enabling urban industrial clusters to expand. In metallurgy, steam engines powered bellows, hammers, and rolling mills, increasing iron output and efficiency. By 1820, Britain's annual pig iron production had risen from approximately 68,000 tons in 1750 to over 500,000 tons, in part due to steam-powered machinery supporting coke-fueled blast furnaces. Mining operations also benefited from steam power, as engines provided reliable drainage for coal, tin, lead, and copper mines. In Cornwall, South Wales, and the Northumberland coalfields, what engines and their derivatives allowed miners to reach deeper seams, expanding accessible reserves. The integration of steam power increased coal output dramatically, which was essential not only for fuel, but also for iron smelting and heating. Steam pumping engines enabled mines to achieve consistent water management, reducing seasonal production variability and enabling a predictable supply of raw materials for industrial consumers. The early adoption of steam power in transport further extended its economic impact. Steam-powered vessels, such as those developed by Henry Bell in Scotland and William Symington in the late 1780s, initiated commercial inland and coastal steam navigation. The first commercially successful steamboat, Robert Fulton's Clermont, began operation in 1807 on the Hudson River in the United States, while British vessels followed in domestic rivers and canals. By the 1820s, steam navigation expanded freight capacity and reduced transport time for raw materials and manufactured goods, reinforcing the industrial integration of regional economies. Rail transport, initially powered by horses and gravity, would later adopt steam locomotion in the 1820s and 1830s, providing a transformative logistical framework for European industrialization. Continental Europe gradually adopted steam power, often several decades after initial British development. In Belgium, the first Watt-type engines were installed in textile and coal mining operations in the 1790s, particularly in the Walloon region. France experimented with steam power for industrial use by the early 19th century, including textile mills along the Loire and in northern industrial centers. In the German states, early steam engines were introduced in the Saxon textile districts and in the mining regions of the Ruhr and Harz Mountains. State involvement in France, Prussia, and Austria facilitated the acquisition and adaptation of British steam technology, often through engineering study tours and licensing agreements, enabling continental industries to adopt mechanized energy while adjusting for local materials, labor structures, and infrastructure. The proliferation of steam engines accelerated technological and mechanical knowledge across multiple industries. In textile manufacturing, what engines powered spinning mules and water frames, maintaining consistent rotational speed and reducing dependency on river flow. In metallurgy, engines powered bellows, trip hammers, and rolling equipment, allowing for higher production rates and improved material quality. Coal mining engines increased extraction depth and volume, supporting the fuel demands of other industrial sectors. By 1830, it is estimated that Britain alone operated several thousand steam engines across manufacturing, mining, and transport sectors, collectively delivering tens of thousands of horsepower and forming the energetic backbone of early industrialization. The economic implications of steam power were profound. Factories could operate on a larger scale, concentrate labor, and maintain continuous production regardless of seasonal or geographic constraints. This increased efficiency reduced production costs, enabling the expansion of domestic and international markets. For example, cotton textile prices in Britain declined steadily during this period, making fabrics accessible to a wider segment of the population while stimulating export markets. Similarly, the availability of steam-powered iron and coal enabled investment in construction, transport, and industrial machinery, promoting secondary industrial development and economic diversification. Labor organization evolved in response to the adoption of steam engines. Mechanized factories required centralized supervision, structured work schedules, and technical operators trained to maintain engines and associated machinery. In Britain, factory managers employed children, women, and men to perform repetitive tasks, often organized around engine-driven operations. Technical knowledge of engine operation, maintenance, and repair became a specialized skill, with apprenticeships and informal training programs developing expertise in thermodynamics, mechanics, and material handling. These labor structures, combined with capital investment in machinery, established a precedent for subsequent industrial sectors reliant on energy-intensive, machine-driven production. The environmental and resource dimensions of steam power also influenced industrial development. The increased use of coal as a primary energy source led to significant rises in extraction and consumption. By 1830, coal production in Britain exceeded 60 million tons annually, with approximately half allocated to industrial use and the remainder to urban heating and domestic consumption. This demand reinforced the economic importance of coal fields and encouraged the development of transport infrastructure, including canals and early railways, to ensure the efficient movement of fuel to industrial centers. Metallurgical production expanded in tandem as coke-fired blast furnaces utilized coal to produce iron for engines, machinery, and construction. The interaction between steam power and technological innovation created a feedback loop. As steam engines increased production capacity, demand for machinery and engineering expertise grew, stimulating further innovation. Engineers such as Richard Trevithick and Arthur Wolff experimented with high-pressure steam engines and compound designs, which allowed greater power output and efficiency. By the 1810s and 1820s, high-pressure engines powered rolling mills, pumping stations, and early steam locomotives. These developments facilitated the transition from water-dominated energy to fully steam-dependent industrial systems, laying the groundwork for subsequent expansion in textiles, metallurgy, transport, and other sectors during the first half of the 19th century. In continental Europe, the diffusion of steam power required adaptation to local contexts. The availability of coal, technical expertise, financial investment, and political support varied widely. Belgium's Walloon coalfields and textile districts provided a conducive environment for Watt-type engines, while France's Loire and Nord regions integrated imported British engines into spinning mills and mining operations. In German states, early steam engine adoption concentrated in Saxony and Silesia, where coal and textile industries were developing. The adaptation often involved modification of engine design to suit local water availability, fuel quality, and workshop practices, demonstrating both technological transfer and regional innovation. By the 1830s, steam engines were widely operational in European industrial centers, though Britain maintained a quantitative lead in both number and horsepower. Steam power also contributed to global economic integration during this period. The mechanization of production, coupled with coal-driven transport innovations, enabled Europe, particularly Britain, to expand exports to colonial and international markets. Steam-powered textile mills produced high-quality cotton cloth, while coal and iron supplied the necessary infrastructure for shipping, canal construction, and early rail transport. Continental European economies, integrating steam engines into textile, mining, and metallurgical operations, gradually increased output for regional and international markets. The early establishment of energy-intensive industrial systems laid the foundation for the broader European Industrial Revolution, which would intensify throughout the 19th century and encompass multiple technological, social, and economic domains. By 1830, steam power had become a central component of industrial energy systems in Europe, driving mechanization, increasing production capacity, and enabling factory concentration. Its introduction transformed labor organization, infrastructure development, and capital investment patterns, linking energy availability directly to economic expansion. From approximately 1770 to 1850, European industrial development was profoundly shaped by advances in iron production, the expanded use of coal, and broader metallurgical innovation. This period witnessed the transformation of iron and coal from relatively localized and artisanal resources into the central elements of industrial infrastructure, enabling mechanized production, transport, construction, and military applications. Britain led the initial phase of this transformation, particularly in coal-rich regions such as the Midlands, South Wales, and northern England, while continental Europe gradually adopted and adapted technological innovations in iron-making, coke utilization, and related metallurgical processes. The demand for iron during the proto-industrial and early industrial phases was driven by mechanized textile production, mining machinery, transport infrastructure, and construction. Traditional iron making relied on charcoal-fueled blast furnaces, which were limited in scale due to the availability of wood and the inefficiency of small furnaces. Charcoal furnaces typically produced a few tons of pig iron weekly, and the quality of iron was variable, constraining its use for machinery and structural applications. The shift to coke, a derivative of coal, enabled larger blast furnaces to operate continuously, using more readily available fossil fuel and reducing dependency on wood. Abraham Darby's pioneering experiments at Coalbrookdale in the early 18th century demonstrated that coke could replace charcoal for smelting iron without compromising quality, providing the technical basis for large-scale industrial iron production. By the late 18th century, coke-fired blast furnaces had become widespread in Britain, particularly in the Midlands and South Wales, allowing production to scale from a few tons per week to tens of tons per week per furnace. By 1800, Britain produced over 200,000 tons of pig iron annually, a substantial increase from the approximately 68,000 tons produced in 1750. The increased output of iron supported the growing demand for machinery, mill components, and industrial tools. This period also saw the introduction of improved furnace designs, including taller blast furnaces with enhanced airflow and lining materials, which increased efficiency and reduced waste. Metallurgical understanding improved through experimentation with fluxes, coke quality, and furnace dimensions, allowing consistent production of malleable iron suitable for forging, rolling, and other applications. The puddling process, developed by Henry Cort in 1784 to 1785, further revolutionized iron production by enabling the conversion of pig iron into wrought iron on an industrial scale. The puddling furnace allowed the removal of carbon from pig iron through repeated stirring in a reverberatory furnace, producing more uniform and workable iron. Coupled with rolling mills, also introduced by Cort in the 1780s, the process enabled the continuous shaping of iron into bars, plates, and structural elements, greatly expanding its applications in construction, machinery, and transport. By 1800, rolling mills in Britain had produced thousands of tons of wrought iron annually, supporting the growth of bridges, machinery, and shipbuilding. Coal, as the primary energy source, was integral to both iron making and mechanized production. Britain's coal production increased from roughly 20 million tons annually in 1760 to over 50 million tons by 1800 and exceeded 80 million tons by 1830. Coal fueled not only iron production but also steam engines, brick kilns, and emerging chemical industries. The shift to coal facilitated energy-intensive industrial processes, allowing for the consistent operation of furnaces, mills, and workshops independent of water sources. By the early 19th century, coal fields in South Wales, Durham, and Lancashire became central to industrial infrastructure, with regional economies increasingly organized around mining and coal transport. Canals, and later railways, were constructed to link coal fields to industrial centers, reducing transport costs and supporting national industrial growth. The integration of iron and coal production created a symbiotic relationship between energy and material resources. Steam engines powered blast furnace blowers, pumping machinery, and rolling mills, while coal supplied the thermal energy necessary for smelting and forging. The availability of iron and coal facilitated mechanization across sectors, including textile machinery, agricultural equipment, and transportation infrastructure such as bridges and early rail tracks. By 1830, Britain's iron output exceeded 1.3 million tons annually, reflecting both technological improvements and increased domestic and international demand. Technological diffusion to continental Europe occurred gradually, with Belgium, France, and the German states adopting British innovations in iron and coal use. In Belgium, the Liège and Walloon regions developed coke-fired blast furnaces and rolling mills by the 1820s, leveraging local coal fields and French engineering knowledge. France, particularly in the Lorraine and Nord regions, combined domestic technical expertise with imported machinery to increase iron output from approximately 30,000 tons annually in 1780 to over 200,000 tons by 1830. In the German states, the Ruhr and Saxon regions expanded production using British techniques, supplemented by local experimentation. Continental iron making often lagged in scale due to less abundant coal, smaller capital accumulation, and political fragmentation, but production nevertheless increased significantly, supporting industrialization, transport networks, and military requirements. The expansion of iron production facilitated infrastructure development critical to industrial growth. Cast iron and wrought iron were used in the construction of bridges, factory frameworks, and canal locks. Notable examples include early cast iron bridges, such as the Iron Bridge over the River Severn in 1779, and subsequent structural applications in factories and warehouses. Iron rails, first introduced in the early 19th century, provided the foundation for the emergence of rail transport, linking industrial centers with resource locations and urban markets. By 1830, over 400 kilometers of rail track had been laid in Britain, facilitating the rapid movement of coal, iron, and manufactured goods, while continental Europe began constructing iron-based transport infrastructure, particularly in Belgium and France. Labor in the iron and coal sectors evolved alongside mechanization and technological innovation. Blast furnaces, rolling mills, and coal mines required a combination of skilled, semi-skilled, and unskilled labor. Skilled metallurgists operated furnaces, controlled smelting processes, and supervised quality assurance, while semi-skilled workers tended machinery and managed material handling. Coal miners performed physically demanding labor, often under regulated shifts dictated by safety and production requirements. Industrial towns associated with iron and coal experienced population growth and urbanization, with worker settlements forming near furnaces, mines, and transport hubs. This concentration of labor enabled knowledge transfer, specialization, and the development of early industrial communities. The economic implications of metallurgical expansion were substantial. Iron became a critical input for industrial machinery, textile production, and transport infrastructure, creating a feedback loop between metallurgical and industrial sectors. The increased supply of iron lowered costs and enabled the construction of larger and more complex machinery, which in turn increased productivity in textiles, mining, and manufacturing. Coal, as both an energy and a metallurgical input, underpinned this industrial growth by providing a stable and abundant fuel source. Investment in the iron and coal sectors stimulated regional economies, with ancillary industries such as brickmaking, engineering workshops, and transport services benefiting from demand. International trade further amplified the significance of iron and coal. British iron and coal supported domestic industrial expansion and were exported to continental Europe and colonial markets. By 1820, Britain exported significant quantities of pig iron and wrought iron to France, the Low Countries, and North America. Continental European states increased domestic production, but also relied on imports to supplement insufficient local supply. Belgium and northern France became net exporters of finished iron products by the 1830s, while German states imported raw iron or coal to feed nascent industrial centers. These trade flows integrated European metallurgical industries into broader economic networks and reinforced industrial linkages across regions. Technological innovation during this period also extended to refining metallurgical processes. The adoption of the reverberatory furnace allowed coke-fueled smelting without contamination from fuel impurities, improving product quality. Steam-powered blowing engines in blast furnaces increased air supply, enhancing combustion and reducing fuel consumption per ton of iron. Metallurgists experimented with chemical additives, furnace linings, and casting techniques to improve consistency, malleability, and strength. The cumulative effect was a steady improvement in the quality and quantity of iron and related products, supporting industrial applications in machinery, transport, construction, and military production. By the mid-19th century, integrated iron and coal industries had become central to industrial economies, particularly in Britain. Coke-fired blast furnaces, rolling mills, and steam-powered pumping engines enabled mass production, while concentrated labor forces in mining and metallurgy formed specialized industrial communities. Continental Europe, adopting and adapting British technology, expanded production to support textile industries, mining, transport, and urban infrastructure. Quantitatively, Britain's annual iron production increased from approximately 200,000 tons in 1780 to over 1.5 million tons by 1850, while coal output exceeded 100 million tons annually. These figures underscore the scale of transformation, linking energy resources, metallurgical innovation, and industrial expansion in a tightly integrated system. The integration of iron and coal production into broader industrial frameworks facilitated subsequent technological developments. Steam engines drove metallurgical machinery, textile spindles, and transport equipment. Metallurgical improvements enabled the construction of stronger machinery, bridges, rails, and factory frameworks. Coal extraction provided the energy necessary for sustained industrial operations, and the feedback loop between resource availability and technological innovation intensified productivity gains. By 1850, Britain had established a dominant position in global industrial production, while continental European states had created the institutional, technological, and economic foundations for sustained industrial growth. Social and institutional adaptations accompanied metallurgical change. Workers in ironworks and coal fields developed specialized technical skills, while labor organizations included hierarchical supervision, apprenticeships, and division of tasks. Urbanization around industrial centers led to the growth of industrial towns with housing, transport links, and local markets for workers' needs. Governments and local authorities increasingly recognized the strategic importance of coal and iron for economic and military purposes, leading to regulatory frameworks, investments in infrastructure, and support for technical education. These institutional developments complemented technological progress, ensuring that production capacity could be effectively scaled and maintained. By 1850, the transformation of the iron and coal industries had fundamentally reshaped the European industrial landscape. Metallurgical innovation, including coke-fueled blast furnaces, puddling, rolling, and steam-powered equipment, enabled high-volume, consistent, and economically viable production. Coal provided the necessary energy to sustain this growth, while the combination of technical, economic, and institutional factors created a framework for industrial expansion across textiles, machinery, transport, and construction. Continental Europe increasingly adopted British innovations, while integrating local resources and expertise to support regional industrialization. This period established the centrality of iron and coal as both materials and energy sources, underpinning the broader trajectory of the Industrial Revolution. The period from 1790 to 1840 witnessed the transformation of Europe's transport and communication systems, which became critical infrastructures supporting industrial expansion, economic integration, and regional specialization. Industrialization created unprecedented demand for the movement of raw materials, fuel, machinery, and finished goods, while population growth and urbanization required reliable and efficient transport networks. Innovations in roads, canals, early steam navigation, and railways, along with the beginnings of electrical telegraphy, reshaped the logistical and informational landscape of industrial Europe, facilitating the diffusion of mechanized production and the integration of regional and national markets. In Britain, road improvements during the late 18th and early 19th centuries laid the foundation for overland transport compatible with industrial-scale trade. Turnpike trusts, operating under statutory authority, constructed and maintained approximately 7,000 miles of improved roads by 1820, facilitating the movement of goods and passengers at reduced cost and time. Innovations included better road surfacing with compacted gravel and stone, improved drainage systems, and standardized road widths. Freight transport via horse-drawn wagons became more efficient, reducing the cost of moving coal, iron, and textiles between production centers and markets. By the 1820s, turnpike roads connected industrial hubs such as Manchester, Leeds, Birmingham, and London, supporting the rapid distribution of raw materials and manufactured goods. Canal construction represented a parallel development in transport infrastructure, enabling heavy bulk goods to be moved more efficiently than overland routes. Britain's canal network expanded significantly between 1760 and 1825, culminating in approximately 4,000 kilometers of navigable waterways by 1830. Notable examples include the Bridgewater Canal, 1761, connecting coalfields in Worsley to Manchester, and the Grand Junction Canal, 1805, linking the Midlands to London. Canals allowed the transport of coal, iron, and textiles at 1/10 the cost of road freight, making industrial expansion economically viable. The use of locks, aqueducts, and inclined planes facilitated elevation changes, while standardized narrowboats optimized cargo capacity. Canal transport supported the concentration of industry in specific regions, linking production centers to coalfields, ironworks, and ports, and stimulating the development of ancillary services such as warehouses, transshipment points, and labor for loading and unloading. Steam power began to influence water transport in the early 19th century, particularly for inland navigation and coastal shipping. William Symington's experimental steam vessels in the 1780s and 1790s demonstrated the feasibility of steam propulsion, while Henry Bell's Comet, 1812, initiated commercial steam navigation on the River Clyde in Scotland. Steamships allowed reliable upstream travel and predictable scheduling, reducing dependence on wind, tides, or river currents. By the 1820s, steam vessels were operating on major rivers such as the Thames, Rhine, and Seine, carrying passengers, raw materials, and manufactured goods. Steam-powered transport increased the volume and speed of trade, connected regional economies, and facilitated industrial supply chains across Britain and continental Europe. Railways emerged as the next significant innovation in transport infrastructure, initially building upon canal and road networks while providing higher speed overland movement of goods and passengers. Early British railways used wooden or iron rails with horse-drawn wagons, evolving to steam-powered locomotion following Richard Trevithick's demonstration of a high-pressure steam locomotive in 1804. The Stockton and Darlington Railway, 1825, marked the first public railway to employ steam locomotives for both freight and passengers, while the Liverpool and Manchester Railway, 1830, established a benchmark for industrial transport, combining high-speed locomotion, scheduled services, and integrated signaling systems. By 1840, Britain had constructed over 2,500 kilometers of railway, providing direct links between coalfields, industrial centers, and ports, enabling rapid, reliable, and bulk transport of materials, machinery, and finished products. Continental Europe observed Britain's transport innovations and gradually adopted similar infrastructure improvements, often adapting to local political, economic, and geographic contexts. In Belgium, the industrial regions of Wallonia and Flanders constructed canals connecting coal and iron production centers with textile regions and ports by the 1820s, while early railways emerged in the 1830s. France initiated canal projects along the Loire, Seine, and Rhone, facilitating the movement of coal, iron, and agricultural produce. The French government, recognizing the strategic importance of industrial transport, subsidized road and canal construction while licensing private entrepreneurs to invest in infrastructure development. German states such as Prussia, Saxony, and Bavaria developed road and canal networks to connect emerging textile and metallurgical centers to coal and iron sources, while the first German steam locomotives and short lines appeared in the late 1830s, supporting industrial integration and interregional trade. The integration of coal, iron, and transport infrastructure created a mutually reinforcing system. Canals and early railways enabled the bulk movement of coal to industrial centers, reducing fuel costs and supporting the expansion of steam-powered machinery. Iron production benefited from improved transport, as blast furnace output, wrought iron, and rails could be distributed efficiently to factories, shipyards, and construction projects. By 1840, Britain's coal fields, including South Wales, Durham, and Yorkshire, were fully integrated with canals, railways, and ports, supporting over 100 million tons of coal production annually. Continental Europe followed similar patterns on a smaller scale, linking industrial regions in Belgium, northern France, and the Ruhr with transport networks that facilitated both domestic use and export markets. Communication infrastructure began to develop alongside transport systems, responding to the need for faster exchange of commercial and technical information. While electrical telegraphy was only in its nascent stage during this period, postal reforms and the establishment of systematic courier networks improved the speed of written correspondence. In Britain, the introduction of uniform postal rates in 1840 facilitated more predictable communication, while continental European states improved post roads, river mail services, and regional courier systems. Efficient communication was essential for coordinating industrial supply chains, managing finance and investment, and disseminating technological knowledge across regions and borders. The expansion of transport and communication systems influenced urbanization and labor patterns. Industrial towns grew around transport hubs, including canal ports, railway junctions, and road intersections. Cities such as Manchester, Birmingham, and Liverpool expanded rapidly, reflecting both the migration of labor from rural areas and the concentration of industry near transport infrastructure. Population growth was accompanied by housing, local markets, and services for workers, forming the early industrial urban landscape. Labor mobility increased as transport networks allowed workers to travel to emerging industrial centers and facilitated seasonal or permanent migration to regions with concentrated employment opportunities. Technological and engineering innovation characterized the construction of transport infrastructure during this period. Canal engineers developed locks, aqueducts, tunnels, and inclined planes to manage elevation changes and optimize navigability. Railway engineers experimented with iron rails, sleepers, gradients, and locomotive design, leading to improved durability, safety, and speed. Bridges and viaducts were constructed using wrought and cast iron, demonstrating the interconnection between metallurgical advances and transport engineering. In Britain, the use of wrought iron in railway bridges and iron rails became widespread by the 1830s, while continental Europe adopted similar techniques in Belgium, France, and Germany. These engineering solutions reflected a combination of scientific knowledge, technical experimentation, and practical adaptation to regional landscapes. Transport infrastructure also affected international trade and market integration. Improved roads, canals, and railways facilitated the domestic distribution of industrial goods, while ports connected by inland transport enabled the export of manufactured products and import of raw materials. Britain exported cotton textiles, iron goods, and machinery to continental Europe, North America, and the Caribbean, relying on integrated transport and port systems to maintain efficiency and cost-effectiveness. Continental European industries, particularly in Belgium and northern France, used canals and early railways to connect industrial centers with domestic and international markets, promoting regional specialization and economic integration. These developments contributed to the emergence of a continental industrial economy interconnected with global trade networks. By 1840, transport and communication revolutions had reshaped Europe's industrial geography. Britain led in the extent and efficiency of its roads, canals, railways, and navigable rivers, providing a model for continental adoption. Coal and iron transport were optimized, enabling high-volume industrial output, while canals and early railways supported regional economic integration. Continental Europe, while initially lagging behind Britain, adopted infrastructure improvements in Belgium, France, and the German states, providing the foundations for expanded industrial capacity in textiles, metallurgy, and emerging manufacturing sectors. The combination of transport and communication networks facilitated specialization, market expansion, and technological diffusion, establishing critical logistical and informational support for industrialization. Economic analysis highlights the scale and impact of transport improvements. Canal freight reduced the cost of coal by as much as 80% compared with road transport, while early railways further decreased transport costs and time. Freight capacity expanded dramatically, with early railways capable of moving tens of tons per train, compared with the few tons per wagon or barge. The ability to move raw materials, coal, and iron efficiently supported industrial output growth, regional specialization, and market integration. Communication improvements, including postal reform and courier systems, ensured coordination of industrial operations and facilitated the spread of technical knowledge, enabling industrial practices developed in Britain to be adopted and adapted in continental Europe. The social implications of transport and communication revolutions were closely linked to industrialization. Urban growth, labor mobility, and regional specialization fostered the formation of industrial communities with organized workforces. Workers could access employment in emerging industrial centers due to improved transport, while merchants and industrialists expanded commercial networks across towns and regions. Communication networks enabled coordination between investors, manufacturers, and suppliers, supporting capital-intensive industrial operations and facilitating technological dissemination. These developments contributed to a more integrated European industrial economy, capable of sustained growth and innovation. By the conclusion of this period, the integration of transport and communication networks had become an essential component of industrial capacity. Roads, canals, steam-powered navigation, and early railways enabled the efficient movement of raw materials, coal, iron, and finished products. Postal and courier systems supported the flow of information, coordination of investment, and dissemination of technical knowledge. Together, these developments underpinned industrial production, regional specialization, and economic expansion across Britain and continental Europe, providing a critical logistical and informational foundation for subsequent technological, social, and economic transformations during the 19th century. Between 1790 and 1850, Europe experienced profound changes in labor organization, urban development, and social structure as industrialization intensified. The expansion of mechanized manufacturing, iron and coal industries, transport networks, and steam-powered machinery transformed traditional work patterns, reshaped communities, and created new social classes. Britain led these transformations, while continental Europe gradually adopted industrial practices, integrating them with local labor systems, urban planning, and political frameworks. This period illustrates the interplay of technology, economic demand, population growth, and institutional adaptation in reshaping labor and society during the early Industrial Revolution. Population growth was a fundamental driver of industrial labor availability. Britain's population increased from approximately 8 million in 1750 to 16.8 million by 1850, reflecting declining mortality, increased agricultural productivity, and higher fertility rates. The transition from rural work to wage labor was central to industrial social transformation. Cottage industries and agrarian employment gradually lost dominance in industrializing regions as mechanized factories required centralized labor and regular schedules. Textile factories, ironworks, coal mines, and metallurgical operations demanded a workforce organized around production schedules rather than seasonal agricultural cycles. In early textile mills, labor hours ranged from 12 to 16 hours per day, 6 days per week, with minimal breaks. Children, women, and men were employed in specialized tasks, including spinning, weaving, carding, boiler operation, and mechanical maintenance. Wage labor provided monetary income, but also imposed strict discipline, reducing autonomy compared with agrarian or domestic labor systems. Child labor was widely used in factories and mines. In Britain, estimates indicate that by 1830, children under 14 accounted for approximately 30% of workers in textile mills and up to 20% in coal mines. Children performed repetitive, low-skill tasks such as piecing threads, cleaning machinery, or tending conveyor belts. Industrial work for children often involved long hours, exposure to machinery hazards, and inadequate nutrition, though it provided families with supplemental income. Legislative responses were initially limited, but the Factory Acts of 1802, 1819, and 1833 gradually established age limits, maximum working hours, and compulsory schooling for younger children, reflecting growing recognition of the social and health implications of industrial labor. Women comprised a significant portion of the workforce, particularly in the textile and domestic industries. In early cotton mills, women often outnumbered men, performing tasks such as spinning, weaving, and finishing. Women's wages were typically lower than men's, ranging from 30 to 60% of male earnings for comparable hours. The employment of women allowed families to supplement household income while meeting the labor demands of mechanized factories. Women also participated in rural proto-industrial cottage production, providing continuity between domestic and industrial labor systems. In continental Europe, similar patterns emerged. In northern France and Belgium, women constituted approximately 40 to 50% of the textile labor force by 1830, while in the German states, women increasingly worked in spinning and weaving operations integrated with mechanized mills. The Industrial Labor Organization introduced hierarchical supervision and technical specialization. Factories implemented strict oversight to maintain efficiency and safety, with managers, foremen, and specialized operators directing work. Skilled labor included machine operators, boiler attendants, engineers, and metallurgists who maintained machinery, managed production quality, and adapted processes for efficiency. Semi-skilled labor performed repetitive tasks or assisted skilled workers, while unskilled labor undertook auxiliary functions such as carrying materials, cleaning, and handling waste products. This division of labor reflected both technological requirements and economic efficiency, increasing productivity and establishing labor hierarchies that structured early industrial society. Urbanization intensified alongside industrial labor expansion. Cities developed around factories, coal mines, and metallurgical centers, creating dense residential districts near industrial sites. Housing was often constructed rapidly and with limited infrastructure, resulting in overcrowding, poor ventilation, and inadequate sanitation. Industrial towns such as Manchester, Birmingham, and Leeds expanded with factory complexes, worker housing, and market areas, while municipal authorities gradually invested in street paving, drainage, and water supply systems. Continental European industrial cities, including Lille, Liège, and Chemnitz, followed similar patterns, reflecting both local economic growth and the need to accommodate labor forces concentrated in industrial regions. The rise of new social classes was a defining feature of the early Industrial Revolution. The industrial bourgeoisie emerged as factory owners, mine operators, and merchants controlling capital, production, and trade. Their wealth and influence increased with industrial output, access to credit, and control over transport and infrastructure. Beneath them, a growing working class comprised factory laborers, miners, and artisans integrated into mechanized production systems. Artisans and small-scale producers faced declining autonomy as mechanized processes reduced demand for traditional skills. The stratification of industrial society created both opportunities and tensions. The working class had regular employment and wages, yet faced long hours, hazardous conditions, and limited social mobility, while the bourgeoisie accumulated capital and political influence linked to industrial expansion. Public health and labor reform became increasingly significant. Urban industrialization produced dense populations, inadequate sewage, and pollution from coal smoke, dust, and industrial effluents. By the 1830s, epidemics of cholera, typhoid, and other infectious diseases were documented in industrial cities, prompting early municipal interventions. Local authorities introduced water supply improvements, street cleaning programs, and waste management, while medical knowledge slowly informed public health policy. Labor reform initiatives, particularly in Britain, responded to factory conditions. The Factory Act of 1833 limited working hours for children aged 9 to 13 to 9 hours per day, required schooling, and appointed inspectors to enforce compliance. The Mines and Collieries Act of 1842 prohibited underground work for women and boys under 10, reflecting evolving recognition of labor risks and the need for regulation. Technological and mechanized work environments shaped skill development and training. Apprenticeships and on-the-job training became essential for operating steam engines, textile machinery, metallurgical equipment, and transport infrastructure. Technical knowledge encompassed machine operation, repair, and safety procedures, as well as understanding production schedules and material handling. The concentration of labor in urban industrial centers facilitated the transmission of knowledge, creating localized technical communities capable of incremental innovation and problem solving. Continental Europe, while initially reliant on imported British expertise, gradually cultivated domestic technical skills through apprenticeships, engineering schools, and state-sponsored technical education programs, particularly in Belgium, France, and the German states. Industrial labor also affected family and gender relations. The need for multiple earners in wage-dependent households led to women and children participating extensively in factory work. Family units adjusted daily routines around factory schedules, with collective labor contributing to household income. Household economies were increasingly intertwined with industrial production, as earnings were contingent on factory performance, wage levels, and regional employment opportunities. Migration patterns reflected these dynamics, with rural families moving to industrial towns to access factory employment and specialized labor, reinforcing urban population growth and contributing to regional labor concentration. Labor mobility increased, both within nations and across borders. Seasonal migration from rural to urban areas provided a flexible labor supply, particularly in textile and agricultural processing centers. In Britain, labor migration occurred from rural northern counties to industrial hubs such as Lancashire and the Midlands. Continental Europe witnessed similar internal movements. Workers relocated from agrarian areas to industrial centers in Belgium, northern France, and the Ruhr. Migration was also international. By the 1830s, skilled engineers, machinists, and metallurgists from Britain and continental Europe sought opportunities abroad, disseminating technical knowledge and facilitating industrial diffusion across the continent and beyond. These movements reinforced labor specialization and contributed to early patterns of transnational industrial expertise. The interaction of industrial labor and social institutions was critical. Trade associations, mutual aid societies, and early labor organizations began to emerge, particularly in Britain. Artisans and skilled workers formed guild-like networks to defend wages, working conditions, and employment rights. By the 1830s, small-scale strikes and petitions were documented in textile centers such as Manchester and Leeds, reflecting collective responses to wage reductions, mechanization pressures, and extended working hours. Continental Europe witnessed similar developments. Belgian and French textile centers experienced labor protests and early associations advocating for worker interests, demonstrating the nascent organization of industrial labor within emerging urban societies. Education and literacy gradually adapted to industrial labor demands. Compulsory schooling was limited initially, but factory-based apprenticeship systems and community education provided essential technical knowledge. Workers needed literacy and numeracy skills to operate machinery, record production data, and manage schedules. In Britain, the Factory Act of 1833 required schooling for children employed in textile mills, marking one of the earliest legal recognitions of education as a complement to industrial labor. Continental states such as Belgium and Prussia developed technical and vocational institutions by the 1830s, creating a foundation for a skilled workforce capable of sustaining mechanized production and industrial expansion. The social transformation of the early Industrial Revolution reflected a complex interplay of labor organization, urbanization, technical skill development, and institutional adaptation. Concentrated industrial employment redefined work patterns, replacing seasonal rural labor with wage-based, mechanized schedules. Urban growth concentrated labor populations near factories, mines, and transport hubs, shaping housing, sanitation, and community structures. The emergence of the industrial bourgeoisie and the working class established new social hierarchies, while labor legislation, public health initiatives, and educational reforms gradually responded to the challenges of industrial society. Continental Europe, although initially lagging in industrial concentration, replicated and adapted British patterns in Belgium, France, and the German states, integrating technological adoption with local labor systems and institutional frameworks. By 1850, the labor and social landscape of industrial Europe had been fundamentally transformed. The widespread use of mechanized factories, steam power, and transport networks reshaped employment, skill development, urban form, and family dynamics. Population growth, urbanization, and labor concentration facilitated both economic productivity and social challenges, prompting early interventions in labor legislation, public health, and education. Continental European industrial regions increasingly mirrored British experience, with specialized labor forces, emerging urban centers, and nascent labor organizations forming the foundation for ongoing industrial development during the second half of the 19th century. Between 1830 and 1870, the process of industrialization spread from Britain to continental Europe, creating new industrial regions, transforming labor systems, and integrating previously localized economies into emerging national and international markets. While Britain had achieved mechanized production, widespread use of steam power, and integrated transport networks by the early 19th century, continental European states faced unique geographic, political, and economic constraints that shaped the trajectory of industrialization. Belgium, France, the German states, and northern Italy became the primary centers of continental industrialization during this period, adopting British technologies while also developing indigenous adaptations to local conditions. Belgium was the first continental European state to industrialize on a substantial scale. The region of Wallonia, with coal fields in the Sambre-Meuse Valley and iron deposits in the Ardennes, provided the raw materials necessary for early industrial development. By the 1820s, Walloon entrepreneurs had established coke-fired blast furnaces, rolling mills, and mechanized textile operations, often employing British engineers and importing machinery. Production increased steadily. Pig iron output rose from approximately 12,000 tons in 1820 to over 100,000 tons by 1850. The textile industry, concentrated in Ghent and Liège, expanded with mechanized spinning and weaving machinery, particularly in cotton and wool production. Railways further integrated these regions with domestic and foreign markets. The Brussels Mechelin Railway, opened in 1835, marked Belgium's first passenger railway and facilitated the distribution of coal, iron, and manufactured goods. By 1870, Belgium's rail network exceeded 2,500 kilometers, supporting rapid industrial and urban expansion. France industrialized more gradually, constrained by political instability, limited coal resources in the north, and regional disparities in capital and infrastructure. Industrialization concentrated in the Nord-Pas-de-Calais region, Lyon, and Alsace-Lorraine. Coal production in northern France increased from approximately 1.5 million tons in 1830 to over 6 million tons by 1870, providing energy for textile mills, ironworks, and chemical production. The iron industry adopted coke-fired blast furnaces and rolling mills, increasing pig iron output from around 100,000 tons in 1830 to more than 400,000 tons by 1870. Textile mechanization expanded in the industrial cities of Lille, Roubaix, and Tourcoing, where cotton, wool, and silk mills employed thousands of workers. Railways, supported by state investment and private capital, connected coalfields, industrial centers, and ports, promoting domestic market integration and exports. The French government actively intervened in infrastructure development, standardizing track gauges, funding canal improvements, and implementing tariffs to protect nascent industries. The German states experienced a heterogeneous industrialization process, shaped by political fragmentation, regional resource distribution, and differing levels of capital accumulation. The Ruhr region of Prussia, Saxony, and the Saarland became early centers of industrial growth. Coal fields in the Ruhr Valley, along with iron ore deposits in the Rhineland, facilitated the construction of coke-fired blast furnaces and rolling mills, initially modeled on British techniques. Saxony, with textile production concentrated in Leipzig, Chemnitz, and Zwickau, adopted mechanized spinning and weaving, particularly in cotton and wool, while maintaining traditional artisan workshops. By 1850, Prussia produced approximately 1 million tons of coal annually, increasing to over 10 million tons by 1870, supporting iron production, railways, and emerging chemical industries. The Zollverein, established in 1834, created a customs union linking most German states, eliminating internal tariffs and fostering a unified market that accelerated industrial investment, railway construction, and interregional trade. Railways were central to continental industrialization. Belgium, France, and the German states adopted British railway technology, including steam locomotion, iron rails, and standardized gauges. By 1850, Belgium had constructed over 2,000 kilometers of track, France approximately 4,000 kilometers, and the German states around 3,000 kilometers. Railways enabled the rapid transport of coal, iron, and manufactured goods, linking industrial centers with ports and raw material sources. The integration of railways with canals and roads reduced transport costs, facilitated regional specialization, and encouraged both domestic and international trade. Continental railways also promoted labor mobility, allowing skilled engineers, mechanics, and workers to migrate to growing industrial regions and disseminate technical expertise. State policy significantly influenced continental industrialization. In France, the government supported infrastructure development, regulated tariffs, and subsidized rail construction. Prussia and other German states invested in technical education, mining schools, and industrial research institutions, fostering a skilled workforce capable of operating mechanized factories, metallurgical plants, and transport networks. Belgium relied on private capital with government support, establishing banks, investment companies, and engineering firms to develop industrial regions efficiently. State involvement in infrastructure and education complemented private entrepreneurship, facilitating the diffusion of technology and the accumulation of industrial capital across continental Europe. Textile mechanization was a primary driver of early continental industrialization. Cotton spinning and weaving expanded rapidly in Belgium, northern France, and Saxony, utilizing machinery imported from Britain or developed domestically. Power looms, spinning mules, and carding machines enabled higher output and reduced labor costs compared with traditional handloom production. In Ghent, mechanized textile mills employed thousands by the 1840s, producing cotton and wool fabrics for domestic and international markets. France's Lyon region specialized in silk manufacturing, integrating mechanized looms with traditional artisanal techniques. These textile centers employed women and children, concentrated labor in urban areas, and generated capital for investment in ironworks, railways, and chemical production. Iron and metallurgical industries expanded in parallel with textile mechanization. Coke-fired blast furnaces, puddling, and rolling processes were adopted to produce structural iron, rails, machinery components, and tools. By 1870, Belgium produced over 200,000 tons of pig iron annually, France over 400,000 tons, and Prussia more than 1.2 million tons. Iron output enabled railway construction, factory frameworks, bridge building, and ship construction, linking metallurgical production with broader industrial expansion. Coal remained essential, with production concentrated near metallurgical centers. Energy-intensive chemical industries, including sulfuric acid and alkali production, emerged in Belgium, France, and Germany, supporting textile processing, mining operations, and metallurgical refinement. Labor organization and social transformation paralleled technological and infrastructural changes. Industrial towns in Belgium, France, and Germany experienced rapid population growth, with concentrations of workers near factories, mines, and transport hubs. Financial and commercial institutions facilitated industrial expansion. Banks, joint stock companies, and investment firms in Belgium and France provided capital for factories, railways, and mining operations. The Banque de Belgique, 1835, and Société Générale, 1822, in Belgium, along with the Credit Mobilier, 1852, in France, financed industrial projects, integrated transport networks, and urban expansion. In the German states, state-sponsored banks and private investment networks supported mining, metallurgy, and railways. Capital accumulation enabled the purchase of machinery, construction of factories, and expansion of transport infrastructure, reinforcing the interdependence of financial institutions, technical innovation, and industrial production. Technological transfer and adaptation characterized continental industrialization. British machinery, particularly textile equipment, steam engines, and metallurgical apparatus, was imported and adapted to local conditions. Belgian engineers modified steam engines to operate efficiently on smaller coal reserves, while French workshops developed domestic production of spinning machines and looms adapted to regional labor and raw materials. German states emphasized technical education to cultivate domestic expertise, establishing polytechnic schools, mining academies, and technical workshops by the 1840s. These measures reduced dependence on British imports and facilitated sustained industrial development within continental economies. By 1870, continental Europe had developed a diverse industrial landscape. Belgium had established integrated coal, iron, and textile sectors supported by railways and financial networks. France had expanded coal and iron production, mechanized textiles, and constructed extensive transport infrastructure. German states, particularly Prussia, Saxony, and the Rhineland, had industrialized mining, metallurgy, textiles, and transport, supported by the Zollverein and state-led technical education. Northern Italy began mechanized textile production in Lombardy and Piedmont, utilizing local water power and integrating with regional trade networks. These developments reflected a combination of imported technology, domestic innovation, institutional support, and capital investment, producing a continent increasingly aligned with industrial principles established in Britain. The interconnection of labor, technology, transport, and capital enabled regional specialization. Coal-producing regions concentrated on energy-intensive production, such as metallurgy and the chemical industries. Textile centers utilized mechanized mills, labor-intensive processes, and regional raw materials. Transport hubs linked production centers with domestic and international markets. Financial and commercial institutions coordinated investment, trade, and infrastructure development. Urban populations grew in tandem, forming industrial communities with specialized labor, nascent social structures, and emerging civic institutions. Continental Europe, by 1870, had established a foundation for continued industrial expansion, technological adoption, and integration into global economic networks. Industrialization in continental Europe also impacted trade and international relations. Belgian and French industrial products, including textiles, iron, and machinery, entered international markets, competing with British exports. German iron and coal exports supplied neighboring states, while regional infrastructure development supported export-oriented production. Transport improvements facilitated both domestic integration and international trade, linking inland industrial centers with ports such as Antwerp, Rotterdam, Le Havre, and Hamburg. Economic interdependence among European states intensified as industrial regions relied on raw material imports, labor mobility, and capital flows from both domestic and international sources. By 1870, continental European industrialization reflected a convergence of technology, labor, infrastructure, and institutional support. Mechanized production, steam power, railways, and integrated finance enabled regional specialization, urbanization, and economic growth. Belgium, France, and the German states had established industrial cores capable of sustained output in textiles, metallurgy, and transport-related sectors, while northern Italy began participating in mechanized textile production. Continental Europe, though initially lagging behind Britain in scale and integration, had developed industrial regions with the technical, financial, and infrastructural capacity to support ongoing industrial expansion, technological innovation, and participation in an increasingly interconnected European economy. The period between 1850 and 1900 in Europe represents the phase commonly referred to as the Second Industrial Revolution, characterized by the intensification and diversification of industrial technologies, the expansion of new sectors, and the integration of science and engineering into large-scale production. This period was distinguished by the widespread adoption of steel, chemicals, and electricity, as well as by the development of new machinery, transport innovations, and communication technologies. Continental European industrial regions, particularly in Germany, France, Belgium, and northern Italy, expanded rapidly, while Britain, already industrially advanced, consolidated and diversified its industrial output. Steel production became central to industrial growth during this period. The introduction of the Bessemer process in 1856, followed by the open hearth Siemens-Martin process in the 1860s, allowed large-scale, cost-effective production of high-quality steel. Britain, which produced approximately 1.2 million tons of steel in 1850, increased its output to over 5 million tons by 1900. Germany emerged as a major producer, with steel output rising from roughly 0.5 million tons in 1860 to 6 million tons by 1900, concentrated in the Ruhr and Saar regions. France and Belgium also expanded steel production, particularly in Lorraine, Liège, and Charleroi, to supply railways, bridges, machinery, and shipbuilding. The availability of steel enabled the construction of railways, factory frameworks, urban infrastructure, and machinery, fundamentally transforming industrial capacity and supporting the growth of heavy industries. The chemical industry developed rapidly, building on both domestic demand for industrial products and the rise of scientific chemistry. Germany led in chemical manufacturing, with companies such as BASF, Bayer, and Hoechst producing synthetic dyes, fertilizers, and chemical intermediates. Synthetic alizarin, produced from coal tar derivatives by 1868, replaced natural sources, while synthetic ammonia for fertilizers emerged in the 1890s. France expanded chemical production in regions such as Alsace-Lorraine and northern textile centers, producing dyes, bleaching agents, and acids. Belgium's chemical industry, concentrated near Liège and Ghent, supplied textiles and metallurgical processes. Chemical innovation supported not only the textile industry, but also agriculture, metallurgy, and emerging consumer goods, reflecting the integration of scientific research and industrial production. Electrical technology began to influence industrial production and infrastructure by the late 19th century. Experiments with electric motors, generators, and lighting, particularly after Michael Faraday's discoveries in electromagnetic induction, led to practical applications in factories and urban utilities. By the 1880s, electric street lighting was installed in Paris, Berlin, and London, while electric motors powered small workshops and mechanized operations. The development of electrical distribution networks enabled new forms of industrial layout, facilitating more flexible factory designs independent of water or steam power. Telegraph and early telephone systems, increasingly integrated with electric networks, improved communication for industrial coordination, finance, and administration. Transport infrastructure advanced significantly during this period, supporting the expansion of industrial networks and international trade. Railways, initially concentrated in Britain and Belgium, extended rapidly throughout continental Europe, particularly in Germany, France, northern Italy, and Austria-Hungary. Germany's rail network expanded from approximately 9,400 kilometers in 1850 to over 62,000 kilometers by 1900, integrating coal fields, steel plants, textile centers, and ports. France's railway mileage increased from 9,800 kilometers to more than 30,000 kilometers in the same period. Railways enabled efficient movement of raw materials such as coal, iron, and cotton, as well as finished goods, facilitating regional specialization and national integration. Steamships, increasingly iron and steel-hulled, powered by coal-fired engines, enhanced overseas trade and complemented railway networks, enabling European industrial products to reach global markets. Mechanization intensified across multiple sectors. Textile production benefited from faster, more efficient power looms and spinning machinery, enabling cotton and wool output to rise dramatically. Germany's cotton industry, particularly in Saxony, doubled production between 1850 and 1870, incorporating mechanized looms and steam-powered spinning operations. Metallurgy expanded through mechanized rolling mills, precision machine tools, and large-scale foundries capable of producing engines, railway components, and bridge structures. Machine tools, including lathes, planers, and drills, facilitated standardization and interchangeable parts, critical for both industrial efficiency and technological advancement. Factories increasingly relied on integrated processes, combining raw material preparation, production, finishing, and distribution within single complexes. The internal combustion engine emerged toward the end of the 19th century, creating the foundation for future transportation and industrial mechanization. Experiments by Etienne Lenoir, Nicolaus Otto, and Gottlieb Daimler produced engines suitable for stationary power and vehicle propulsion. Although widespread adoption occurred in the early 20th century, the period 1850 to 1900 saw the development of prototypes and early commercial engines that influenced industrial machinery, agricultural equipment, and transport vehicles. These innovations complemented the ongoing use of steam power while setting the stage for rapid technological expansion in subsequent decades. Labor and social organization continued to evolve in response to industrial intensification. Urban populations in industrial centers expanded rapidly. Berlin's population grew from approximately 400,000 in 1850 to over 1.3 million by 1900. Manchester increased from 300,000 to 700,000, and the Ruhr cities collectively grew from around 400,000 inhabitants to more than 1.5 million. Factory labor became increasingly specialized, with divisions between skilled operators, semi-skilled technicians, and unskilled workers. Women and children continued to provide substantial portions of the workforce, particularly in textiles, food processing, and light manufacturing, while men dominated heavy industry, mining, and railway work. Working hours ranged from 10 to 12 hours per day by mid-century, and gradually reduced through labor reforms, union negotiations, and regulatory legislation. The emergence of industrial corporations and capital-intensive enterprises reshaped economic organization. Joint stock companies, particularly in Germany and France, facilitated large-scale investment in railways, steel production, and chemical manufacturing. In Germany, the founding of large corporations such as Krupp and Essen enabled centralized management, coordinated investment, and mass production of steel, artillery, and machinery. French enterprises, including Schneider Kreuzott, expanded metallurgy and engineering production, supplying domestic and colonial markets. Belgium's industrial sector relied on partnerships between entrepreneurs, banks, and state authorities to finance integrated industrial and transport networks. The scale of these enterprises required extensive financial management, labor coordination, and technical expertise, reflecting the complexity of industrial capitalism during this period. Scientific and technical education became increasingly important. Germany, in particular, invested heavily in technical universities, mining academies, and industrial research institutions. By the 1870s, the German educational system produced skilled engineers, chemists, and metallurgists capable of operating complex machinery, designing chemical processes, and managing industrial enterprises. France followed a similar trajectory with École des Mines, École Polytechnique, and specialized technical schools, while Belgium established engineering schools in Liège and Ghent. Britain, already technologically advanced, supplemented practical apprenticeships with formal technical training. The integration of education and industrial practice facilitated innovation, productivity, and the adaptation of new technologies. International industrial diffusion was increasingly evident. European industrial products, particularly steel, chemicals, and machinery, were exported to North America, Latin America, and Asia. Continental Europe imported raw materials, including cotton from Egypt and India, iron ore from Spain and Sweden, and coal from Britain, creating integrated industrial supply chains. The coordination of production, transport, and finance across borders reflected the growing globalization of industrial production. European technical expertise and machinery were also exported, enabling industrial development abroad while reinforcing Europe's dominance in global industrial markets. Urbanization and social change accompanied technological intensification. Industrial cities required expanded housing, public services, and infrastructure to accommodate growing populations. Overcrowding, pollution, and sanitation challenges were addressed gradually through municipal investments, state legislation, and public-private initiatives. Labor organization evolved, with trade unions emerging in Britain, Germany, and France to represent workers' interests, advocate for wage improvements, regulate working conditions, and negotiate shorter working hours. Social stratification became more pronounced, with a wealthy industrial bourgeoisie controlling capital and management, a skilled technical middle class of engineers and supervisors, and a growing urban working class concentrated in factories and industrial districts. The integration of transport, communication, and production technologies accelerated regional specialization and economic growth. Coal and steel production concentrated in the Ruhr, Saar, Wallonia, and northern France. Textiles focused in Saxony, Lancashire, northern France, and Belgium. Chemical production expanded in Germany, France, and Belgium, and machine tool and precision engineering industries emerged in Germany, Britain, and Switzerland. Railways, canals, and steamships facilitated the movement of raw materials to factories and finished products to domestic and international markets. Telegraph networks and early telephones improved coordination across enterprises, enabling complex industrial and commercial operations on regional, national, and international scales. By 1900, Europe's industrial landscape had undergone substantial transformation. Germany surpassed Britain in chemical production and rapidly approached its steel output. France maintained strong textile and metallurgy sectors. Belgium consolidated coal, iron, and textile industries, and Britain diversified into machinery, chemicals, and consumer goods. Technological innovation, urbanization, and the organization of labor and capital had created integrated industrial economies capable of sustaining mass production, technological research, and global trade. This period laid the foundation for continued industrial expansion in the 20th century, the emergence of mass markets, and the consolidation of Europe as the primary industrial and technological center of the globe. Between 1850 and 1914, European industrialization reached a stage characterized by large-scale capital formation, the rise of corporate enterprises, and increasingly structured governance of industrial economies. The consolidation of financial resources, organization of production, and state involvement in infrastructure and education became critical to sustaining industrial growth. Across Britain, Germany, France, Belgium, and northern Italy, economic and institutional innovations complemented technological developments, allowing the expansion of heavy industry, transport networks, and consumer-oriented manufacturing. Industrial capital intensified in scale and scope during this period. Joint stock companies became the primary mechanism for pooling investment to fund large-scale industrial and infrastructural projects. In Germany, the establishment of corporations such as Krupp, Siemens, and AEG enabled the coordination of steel production, electrical machinery, and heavy engineering. Krupp, headquartered in Essen, employed over 30,000 workers by the 1890s and produced artillery, railway engines, and industrial machinery for both domestic use and export. Siemens expanded electric telegraphy, lighting, and power distribution throughout Germany and abroad. In Britain, joint stock companies invested in railways, coal fields, steelworks, and chemical industries, facilitating the efficient mobilization of capital. France saw the emergence of industrial conglomerates, including Schneider Kreutzat, producing armaments, metallurgical equipment, and machinery for civil and military applications. The organization of capital required innovations in banking and finance. European banks increasingly specialized in industrial lending and long-term investment, creating connections between savings, capital formation, and industrial enterprise. In France, Crédit Lyonnais, founded in 1863, and Crédit Mobilier, established in 1852, financed railways, steel, and mining operations. In Belgium, the Société Générale de Belgique provided long-term capital for coal, iron, and railway projects. In Germany, state-backed banks, regional credit institutions, and private banks provided the liquidity necessary to finance technological expansion, industrial consolidation, and export-oriented production. These financial institutions also facilitated international trade, currency exchange, and investment flows, integrating European industrial economies with global markets. Industrial organization shifted toward hierarchical, bureaucratic structures capable of managing complex operations. Factories, mines, and transport networks employed layers of management to supervise production, labor, and logistics. Engineers, accountants, and clerical staff became integral to operations, supporting efficiency, cost control, and quality assurance. Mechanized production, particularly in steel, chemical, and textile sectors, required standardized processes, precision engineering, and coordinated supply chains. The scale of enterprise demanded attention to procurement of raw materials, storage, maintenance of machinery, and distribution of finished goods, creating an industrial administrative class distinct from both laborers and owners. Labor management evolved alongside corporate expansion. Industrial firms developed systematic wage policies, hierarchical supervision, and internal discipline to maintain productivity. Factory managers implemented timekeeping systems, specialized shifts, and task segmentation. In the chemical, steel, and heavy engineering sectors, skilled labor became essential, with engineers and technicians overseeing complex machinery and processes. Trade unions and early labor organizations emerged as workers negotiated wages, hours, and conditions, influencing corporate policies indirectly while prompting incremental regulatory reforms. Women and children remained significant portions of the workforce, particularly in textiles, food processing, and light manufacturing, though their employment in heavy industry remained limited to unskilled and semi-skilled tasks. Governments increasingly participated in industrial governance, infrastructure development, and technical education. In Germany, the state actively supported the development of industrial districts through technical schools, polytechnics, and mining academies. By 1900, Germany operated over 30 polytechnic institutions producing engineers, chemists, and technical specialists, fostering domestic innovation and reducing reliance on foreign expertise. France maintained École Polytechnique and Écoles de Mines, which trained engineers for industry, mining, and railways. Belgium's engineering schools in Liège and Ghent provided skilled labor for metallurgy, railways, and textile machinery production. In Britain, technical training supplemented apprenticeships, particularly in electrical, mechanical, and chemical industries, supporting continued industrial leadership. Infrastructure development was central to industrial governance. European governments provided capital, regulation, and planning for railways, canals, ports, and urban utilities. Germany's national rail network expanded rapidly under state supervision, facilitating the movement of coal, steel, chemicals, and manufactured goods. France consolidated railway construction with standard track gauges, integration of regional lines, and government oversight of private railway companies. Belgium, though primarily reliant on private investment, benefited from government support in legal frameworks, infrastructure planning, and financial guarantees. Transport infrastructure integrated regional economies, facilitated specialization, and enhanced domestic and international trade, reflecting the close coordination between industrial capital and state governance. Industrial expansion encouraged technical standardization, particularly in machinery, railways, and production processes. Machine tools, standardized parts, and modular production allowed factories to scale efficiently, produce interchangeable components, and reduce costs. Germany led in precision engineering, producing standardized machinery, electrical equipment, and chemical apparatus for domestic and international markets. Britain maintained leadership in mechanical engineering, particularly in textile machinery, locomotive production, and naval architecture. France emphasized both metallurgy and mechanical engineering, producing industrial and military equipment for domestic needs and colonial deployment. Standardization allowed multinational industrial firms to coordinate production, export machinery, and support large-scale infrastructure development across borders. Corporate governance also encompasses mergers, cartels, and industrial associations. In Germany, cartels coordinated production, stabilized prices, and regulated competition in coal, steel, chemicals, and electrical industries. The Ruhr Coal Cartel, established in the 1870s, exemplified collective industrial management, balancing supply, demand, and investment among competing firms. French industries experimented with syndicates and professional associations to manage competition and technological diffusion. In Britain, formal cartels were less prevalent, though informal agreements among industrial firms influenced market behavior. Cartels and associations represented attempts to stabilize industrial growth, protect capital investment, and integrate complex production and distribution networks in a rapidly expanding industrial landscape. Industrial-era governance extended to regulatory oversight, safety, and labor legislation. Governments gradually implemented factory acts, sanitation regulations, and workplace safety standards. Britain's Factory Acts of 1833, 1844, and subsequent legislation limited working hours for women and children, mandated inspection, and required basic sanitation. Continental Europe introduced similar reforms. France's 1841 law restricted child labor. Germany implemented occupational safety regulations in the 1870s, and Belgium mandated factory inspections and minimum standards for working conditions. Industrial governance, therefore, combined corporate organization with state regulation to maintain productive labor, secure investment, and mitigate social unrest while allowing continued industrial expansion. Industrial enterprises increasingly integrated research and development into production. Germany pioneered the combination of university research, industrial laboratories, and corporate innovation. Companies such as BASF and Siemens maintained laboratories for chemical analysis, electrical experimentation, and process optimization. British firms, including engineering and textile companies, incorporated technical expertise into operational management, though formal R&D laboratories were less centralized than in Germany. French industry emphasized applied research in metallurgy, textiles, and chemicals, often coordinated with state-supported institutions. The integration of research, technical education, and production allowed industrial firms to innovate rapidly, reduce costs, and maintain competitive advantage in domestic and international markets. Urbanization, finance, and industrial governance were interdependent. Expanding industrial centers required municipal investment in housing, sanitation, water supply, and transport infrastructure, often coordinated with state policy and industrial capital. Urban populations in Ruhr, Liège, Lyon, and Milan grew dramatically, creating demand for goods, labor, and municipal services. Banks, insurance companies, and investment firms provided credit for construction, industrial expansion, and urban development. Municipal authorities collaborated with industrial corporations to develop urban amenities, manage social issues, and maintain public order, reflecting the integration of capital, governance, and industrial development in European economies. The international dimension of industrial-era governance became increasingly important. European industrial firms exported machinery, chemicals, textiles, and engineering products globally, integrating domestic production with colonial and foreign markets. British, German, French, and Belgian firms supplied railways, steel, and electrical infrastructure to regions in South America, Asia, and Africa. Governments supported industrial expansion with trade policies, standardization, and technical assistance, often facilitating colonial infrastructure and raw material extraction. Global industrial integration reflected the interdependence of corporate organization, technical expertise, capital formation, and state policy, consolidating Europe's economic dominance during the late 19th and early 20th centuries. By 1914, industrial capitalism in Europe had reached a mature stage. Large-scale capital, joint stock corporations, banking institutions, state involvement in infrastructure and technical education, and industrial standardization underpinned an integrated, high-output industrial economy. Germany, Britain, and France led in heavy industry, machinery, and chemicals. Belgium excelled in coal, steel, and textiles. Northern Italy developed mechanized textiles and integrated metallurgical production. Industrial governance, both corporate and state-based, coordinated production, finance, labor, and infrastructure to sustain technological innovation, international trade, and urbanization. Capital-intensive industrial structures, hierarchical management, and state policy formed the basis of modern industrial economies, establishing frameworks for technological, social, and economic expansion into the 20th century. Between 1850 and 1914, European industrialization became increasingly dependent on global material networks and imperial economic systems, integrating raw material extraction, labor, and markets from Asia, Africa, the Americas, and Oceania into European industrial production. The expansion of industrial infrastructure, particularly railways, shipping, and telecommunication systems, facilitated the efficient flow of raw materials to European industrial centers while supporting the export of manufactured goods. European industrial economies, primarily Britain, Germany, France, Belgium, and to a lesser extent Italy, relied on a combination of colonial acquisition, international trade, and technological innovation to sustain industrial growth during this period. Coal, iron, and steel production underpinned industrial expansion, but European resources were insufficient to meet growing industrial demand, necessitating global sourcing. Britain, for instance, imported significant quantities of iron ore from Spain, Sweden, and North Africa, while Germany sourced iron ore from Lorraine, Sweden, and later Spain. Coal was primarily domestic, but Britain's exports of coal fueled industrial development in continental Europe, North America, and Asia. The extraction of bauxite for aluminum production, copper for electrical wiring, and tin for alloy and industrial applications increasingly relied on overseas colonies. Belgium's industrial centers in Liège and Charleroi imported copper and tin from the Congo Free State, while France sourced aluminum from West Africa and bauxite-rich colonies in the Mediterranean. These flows integrated resource-rich colonies and foreign territories into European industrial supply chains, reflecting the interdependence of global material availability and European production capacity. Cotton remained a central raw material, with European textile industries dependent on overseas production. Britain, the leading textile manufacturer, imported approximately 3 million bales of raw cotton annually by the 1870s, primarily from the United States, India, and Egypt. Continental textile producers, particularly in Belgium, France, and Germany, also relied on imported cotton. The American South supplied the majority of raw cotton until the disruption of the Civil War, 1861 to 1865, after which India and Egypt expanded production under European commercial influence. Egypt, under British and French financial oversight, increased cotton acreage from approximately 1.2 million feddans in 1860 to over 3 million feddans by 1900, directly supplying European textile mills. This global sourcing of raw materials ensured continuous mechanized textile production, linking colonial agricultural labor and European industrial output. Sugar, rubber, and other raw commodities became increasingly significant for industrial and consumer markets. Caribbean colonies, including British and French territories, supplied sugar for refining and industrial consumption, while Brazil exported raw sugar for European processing. Natural rubber, essential for industrial applications such as hoses, tires, and belts, was sourced primarily from Southeast Asia, particularly the Dutch East Indies and British Malaya, by the late 19th century. European companies maintained plantations and commercial networks to secure a consistent rubber supply, supporting the mechanization of transport, mining, and manufacturing operations. These commodities were integrated into European industrial economies, highlighting the global reach of industrial material dependencies. Metallurgical industries depended on imported ores and metals. Copper, essential for electrical generation, wiring, and industrial machinery, was imported from Chile, Spain, and Belgium's colonies. Tin and lead were imported from Southeast Asia and South America. Aluminum, increasingly used in industrial machinery and transport, relies on bauxite extracted in West Africa and the Mediterranean, processed using electricity-intensive methods developed in Europe. Coal, steel, and chemical production also relied on overseas inputs, particularly sulfur and nitrates from South America, for fertilizers and industrial chemicals. This integration of global resources enabled the sustained expansion of European industrial capacities in heavy industry, chemical manufacturing, and mechanized production. Transportation networks were critical to the management of global material flows. Steamship technology, iron and steel hulls, and coal-fired engines facilitated regular transoceanic transport of raw materials, while European ports, Liverpool, Rotterdam, Antwerp, Hamburg, Marseille, and Le Havre, served as hubs for collection, storage, and distribution. Railways within colonies and dependent regions, often constructed with European technical expertise and capital, ensured efficient inland transport to ports for export. In India, British constructed railways integrated cotton-producing regions with Bombay, Calcutta, and Madras ports. In the Congo Free State, Belgian-built railways and river steamer networks transported copper, ivory, and rubber from inland regions to the Atlantic coast. Telegraph and early telephone systems coordinated industrial logistics across continents, enabling European manufacturers to manage supply chains with unprecedented efficiency. Colonial policies were aligned with European industrial priorities. Britain, France, Germany, and Belgium implemented systems of economic administration, taxation, and infrastructure investment to facilitate the extraction of raw materials and control of labor. The British Raj standardized railways, ports, and telegraphs to integrate India's economy into global commodity markets. French colonial administrators in Indochina, West Africa, and Madagascar promoted cash crop agriculture for export to French factories. Belgium's administration in the Congo focused on resource extraction, particularly rubber and copper, utilizing forced labor systems to meet European industrial demand. German Southwest Africa and East Africa were similarly oriented toward resource extraction to support European industrial expansion. These policies ensured that colonial economies supplied raw materials at controlled costs, supporting European industrial growth and global competitiveness. Labor systems within colonial economies reflected European industrial imperatives. Indigenous populations were increasingly integrated into wage labor or coerced labor regimes to ensure consistent production of raw materials. In India, peasants engaged in cotton, indigo, and jute cultivation under contractual obligations to colonial intermediaries. In the Congo Free State, rubber and copper extraction relied on forced labor quotas enforced by colonial authorities, while infrastructure projects employed both local and imported labor under European supervision. Southeast Asian plantations, particularly for rubber and tin, combined migrant labor with European management. Labor-intensive extraction complemented mechanized European processing, linking global human resources with industrial outputs in Europe. Industrial networks were increasingly multinational. European firms established subsidiaries, joint ventures, and trading companies in colonies and dependent regions to secure raw materials and manage commercial flows. German chemical firms, including BASF and Bayer, established overseas offices to coordinate the supply of dyes, chemicals, and fertilizers. British textile firms maintained agency networks in India and Egypt to manage cotton procurement, while Belgian companies established operations in the Congo Free State. These networks ensured stability of supply, technical support for extraction, and integration of raw materials into European industrial production, illustrating the globalization of industrial enterprise. Global markets influenced technological and industrial strategies. Europe's dependence on imported raw materials encouraged investments in mechanization, transportation efficiency, and logistical coordination. In response to cotton shortages during the American Civil War, European manufacturers expanded alternative sources in India, and Egypt adopted improved spinning and weaving technologies to increase yield and diversified fiber inputs. Similar strategies were applied to metals, rubber, and chemical inputs, with European technological and financial capacity determining the efficiency of global resource mobilization. Industrial demand shaped colonial agriculture, mining operations, and infrastructure development, creating a symbiotic relationship between European industrial growth and global material networks. The integration of raw material flows with European industrial production reinforced the interdependence of metropolitan and colonial economies. Railways, ports, and steamships enabled the continuous export of raw materials to factories, while European technological expertise, machinery, and capital investment ensured efficient extraction and processing. Industrial output in Europe, particularly textiles, steel, chemicals, and machinery, relied on the steady supply of global commodities. Simultaneously, European products entered colonial markets as consumer goods, industrial equipment, or transport infrastructure, creating a feedback loop linking production, trade, and investment across continents. Technological innovations within Europe enhanced the management of global material networks. Telegraph systems, standardized shipping schedules, and rail networks facilitated communication, transport, and coordination. European engineers and managers applied scientific methods to resource extraction, industrial processing, and logistics, ensuring reliable integration of distant supply chains into domestic industrial processes. Chemical processes, mechanized production, and improved metallurgy allowed more efficient use of imported raw materials, while electricity and mechanical innovations enhanced factory productivity and transport infrastructure efficiency. By 1914, European industrialization was deeply embedded in global material and labor networks. Britain, Germany, France, and Belgium depended on raw materials sourced from the Americas, Asia, Africa, and Oceania to sustain industrial production. Industrial corporations managed multinational operations to secure supply, coordinate production, and distribute manufactured goods. Colonial policies, infrastructure investment, and labor systems facilitated extraction and ensured the flow of essential resources. European industrial economies had developed highly integrated systems linking domestic production, global resource procurement, and international markets, enabling sustained industrial expansion, technological innovation, and economic dominance during the late 19th and early 20th centuries. From 1850 to 1914, the European Industrial Revolution entered its final phase, in which the social, political, and legal frameworks of industrial societies became increasingly formalized. Industrialization, urbanization, and technological intensification had created profound changes in labor, demographics, and public administration, necessitating reform, regulation, and organized social negotiation. This period saw the emergence of structured labor movements, social welfare legislation, political parties oriented toward industrial labor, and evolving government intervention, setting the stage for the systemic disruptions of the First World War. Population growth and urbanization accelerated social transformation in industrial regions. Between 1850 and 1910, urban populations in Europe expanded significantly. Berlin grew from approximately 400,000 inhabitants to over 2 million. London increased from 2.3 million to 7 million, and Paris rose from 1.2 million to 2.7 million. Industrial cities in Germany's Ruhr, France's Nord-Pas-de-Calais, Belgium's Liège and Charleroi, and northern Italy's Milan and Turin experienced similar growth. Rapid urbanization created high-density living conditions, with limited sanitation, water supply, and housing. Municipal authorities, often in coordination with state governments and private industrial firms, expanded urban infrastructure, including sewerage systems, potable water distribution, gas lighting, and urban transport. The complexity of urban administration increased in proportion to industrial growth, integrating public health measures, transportation planning, and policing into the industrial economy. Labor organizations became increasingly structured. Trade unions, initially local and informal, developed into national and international organizations during the late 19th century. In Britain, the Trades Union Congress, founded in 1868, coordinated representation for multiple industrial sectors, negotiating wages, working hours, and conditions. Germany saw the rise of unions affiliated with the Social Democratic Party, SPD, which was formally established in 1875, representing industrial workers in mining, steel, chemicals, and textiles. France's Confédération Générale du Travail, CGT, formed in 1895, similarly organized workers across sectors. Belgium and northern Italy developed comparable labor associations linked to socialist political movements. Collective bargaining, strikes, and labor negotiations became increasingly prominent in mediating industrial relations, reflecting the growing political influence of the working class. Child labor, female labor, and industrial working conditions prompted legislative reform across Europe. Britain's Factory Acts, including those of 1878 and 1891, limited working hours for children and women, mandated compulsory education for children under 12, and required workplace safety inspections. Germany's industrial legislation, beginning in the 1870s, regulated factory working conditions, restricted child labor, and introduced accident insurance through the 1884 and 1889 social laws initiated under Chancellor Otto von Bismarck. France's laws in 1874 and 1892 limited child labor, mandated factory inspections, and established minimum hygiene and safety standards. Belgium and northern Italy adopted similar legislative measures, reflecting a broader European trend toward formal industrial labor regulation. These reforms gradually improved working conditions while maintaining the overall productivity required for industrial expansion. Social policy evolved to include public health, welfare, and education, with state intervention expanding in industrial centers. Germany pioneered social insurance programs. By 1883, health insurance covered wage earners in industrial sectors. By 1884, accident insurance protected workers injured in factories, mines, or railways. And by 1889, old age and disability pensions were introduced for industrial workers. France, Belgium, and Britain implemented partial welfare measures, such as public health campaigns, municipal support for housing, and compulsory education. though national insurance programs were less comprehensive than in Germany. Industrial societies increasingly recognized the link between worker health, productivity, and social stability, integrating policy into urban governance and corporate management. Industrial labor demographics shifted in response to mechanization, sectoral specialization, and urbanization. Skilled industrial workers became concentrated in machinery, chemical production, and metallurgical operations, while semi-skilled and unskilled workers were employed in textiles, construction, and food processing. Women continued to comprise substantial portions of the workforce in textiles, clothing, and light manufacturing, representing between 20 and 40% of industrial labor in Britain, Germany, and France by the late 19th century. Child labor persisted, particularly in textiles, mining, and light manufacturing, though reforms gradually reduced the proportion of children under 14 in industrial employment from approximately 15 to 20% in 1850 to under 10% by 1910. Wage differentials, occupational hazards, and living conditions remained critical social issues, prompting ongoing advocacy by unions, socialists, and reformist legislators. Political organization reflected the growing social and economic influence of industrial workers. Socialist and labor-oriented parties emerged across Europe. The SPD in Germany, the French section of the Workers' International, SFIO, in 1905, and the Italian Socialist Party, PSI, in 1892. These parties advocated for labor legislation, social welfare programs, universal suffrage, and representation within parliamentary structures. In Britain, the Labour Representation Committee, founded in 1900, coordinated industrial representation in national politics. Labor movements and socialist parties increasingly influenced policy, municipal governance, and national legislative agendas, contributing to systematic reform of industrial societies while negotiating with corporate and state authorities. Industrial politics also intersected with state intervention in economic and technical matters. Governments continued to expand infrastructure, including railways, ports, telegraphs, and urban utilities, while establishing technical education and research institutions to support industrial innovation. Germany's technical universities, polytechnics, and mining academies trained engineers, chemists, and administrators to manage industrial enterprises. France, Belgium, and northern Italy maintained similar institutions. State involvement extended to standardization of weights, measures, and industrial processes, reflecting an increasingly bureaucratized and coordinated industrial governance system capable of sustaining large-scale production and export capacity. International labor and social reforms reflected the transnational nature of industrial economies. The International Workingmen's Association, First International, 1864 to 1876, and subsequent Second International, founded 1889, facilitated the exchange of labor practices, political strategies, and industrial legislation among European and global labor movements. Labor conferences, international congresses, and trade union coordination encouraged the adoption of collective bargaining practices, limits on working hours, and protective labor legislation across multiple countries. European industrial economies, increasingly connected through global trade, capital flows, and technological diffusion, experienced parallel social and political reforms reflecting shared industrial challenges. Urban housing, public health, and sanitation remained critical in industrial centers. Cities like Manchester, Birmingham, Berlin, and Paris invested in sewerage systems, potable water distribution, waste management, and municipal housing. Industrial enterprises contributed to housing construction for workers, particularly in Germany and Belgium, through company towns or subsidized housing. Public health campaigns targeted infectious disease control, child nutrition, and urban hygiene, integrating municipal administration with industrial labor management. Urban planning and public infrastructure evolved as integral components of industrial governance, supporting workforce stability and enhancing productivity in densely populated industrial centers. Education and technical training became increasingly linked to industrial and social policy. Compulsory primary education was introduced across Europe. In Germany by 1871, France between 1881 and 1882, and Belgium in 1914. Secondary and technical education expanded to supply skilled industrial labor, with polytechnics, mining academies, and specialized schools training engineers, chemists, and technical managers. Technical education contributed to industrial innovation, efficiency, and competitiveness, while providing a social mechanism for upward mobility in industrial societies. Integration of education, labor organization, and industrial policy reflected the maturation of European industrial economies in the late 19th and early 20th centuries. Industrial reform and social legislation were complemented by regulatory frameworks governing corporate activity, workplace safety, and urban administration. European governments established inspection systems, mandated accident reporting, regulated chemical and metallurgical hazards, and enforced compliance with labor laws. In Germany, industrial regulation was closely linked with social insurance programs and technical education, creating a coordinated approach to industrial governance. France, Belgium, and Britain adopted similar regulatory frameworks, though with varying degrees of centralization and enforcement capacity. Industrial societies became increasingly reliant on codified legislation, bureaucratic oversight, and coordinated administration to manage the social, economic, and technical dimensions of industrialization. By the early 20th century, industrial societies had developed interconnected systems of labor representation, social reform, corporate management, and state intervention. Industrial labor movements, welfare legislation, and political organization represented structured responses to the social challenges of mechanized production and urbanization. Corporations and state authorities coordinated infrastructure, technical training, and regulatory frameworks to maintain productivity and social stability. European industrial economies were thus integrated internally and externally, linking industrial output with labor management, urban governance, technical innovation, and global material networks. The outbreak of the First World War in 1914 marked a definitive breakpoint in this phase of industrial history. European economies were mobilized for wartime production, restructuring industrial priorities toward military manufacturing, raw material allocation, and logistical coordination. The war disrupted trade, redirected labor forces, and altered patterns of industrial investment. Pre-war social policies, labor negotiations, and industrial governance structures were challenged by state-directed economic planning and mass mobilization. While industrial technology, corporate organization, and social reform had reached a mature stage by 1914, the conflict fundamentally reorganized European industrial economies and redirected the trajectory of industrial development into a new historical phase.